Okay, so let's look at what is methods of sections to calculate the member force. So this is to use when only a few members of a truss are to be found. Okay, consists of passing an imaginary sections through truss. Okay, thus cutting it into two parts. Okay, at the parts that we want to determine the members, they will cut it. So provide the entire truss is in equilibrium, so each of the two parts must also in equilibrium. Okay, so when the system is in the equilibrium system, so even we cut it into two parts, so both parts will be in equilibrium. So therefore, the three equations of equilibriums may be applied to either the one of these two parts to determine the forces at the cut section. So this is as usual, we have total Fx equal to 0, Fy equal to 0, and moment equal to 0. Okay, so what is the procedure of analysis? Okay, so first we need to determine the truss is either determinate or indeterminate by using the stability and determinacy equations. Okay, so this is just same as a joint method, that first we must determine the truss type. Okay, and then we calculate the support reaction, also same as before. We need to get the support reaction if it is not provided. Okay, and then we need to make decision to how to cut it. Okay, through the members where forces are to be determined. So we need to judge and we need to do it ourselves on how to cut it. Okay, so we need to draw the free body diagrams. Okay, after we decide to cut it, then we need to draw the free body diagram of the parts that the truss, whether left or right section. We cut it into two sections, so of course it will have either left or either right. Okay, so which has least members of forces on it. So we need to cut and then we need to make the judgment that have least members of forces. So moment should be sum about at the point, okay, where lies at the intersections of the line of actions of two unknown forces. So when we want to use the equilibrium system for the moment, we will choose that, okay, that the intersection of the line action of only two unknowns, not more than that. Okay, the third unknown forces is determined direct from the equations. Okay, so let's look at the example. So this example 6, determine the force of member BC, CG and FC. So we can see that BC is here, okay, CG is here, and then FG is here. We want to determine these three member forces. So what we have to do is we cut at this point A at here. Okay, so this is the part 1 and this is the part 2. Okay, and then state the member are in the tensions or in the compression. So tension will be in positive, compression in negative. This is okay, this one is same as the previous sections. Okay, so let's look at the truss. Is statically determinate or statically indeterminate? We need to calculate. So from just now the sections, member is 11, reaction is 3, joint is 7. So when you calculate, you put into the equations, 14 is equal to 14, means it's statically determinate. Okay, and then we look at this cut section. We will take these least forces sections, remember. Okay, so we will have the part A, B, part A, okay, the joint A, B, G, and here you have a C here. Okay, this is a C here. Okay, and this is a F here. Okay, if you cut, you will have this. So this is FBC, okay, FGC, FGF. Okay, you want to find these three forces. Okay, so what we can do it here is, okay, total, we need to use the three equilibrium equations to remember. Okay, so you can look at this. Okay, so how you want to find this? So we can use the first equation is the total moment at G equal to 0, because it is in equilibrium, so the moment will be 0 at the point at each joint. Okay, so negative 100, okay, at this point, at point G. Okay, so let me erase this for clearer message. Okay, so at this point G, you can see that, okay, so the moment it will cause only from this A, okay, which is counterclockwise, is negative 100 times 2, the distance, and then plus only FBC, okay, towards this is positive. Okay, so only these two are causing the bending moment at point G. Okay, remember moment is the force times distance. Okay, so for these two, FGC and FGF, they are no distance because they are start from the point G. So that's why these two forces are not causing any moment. Okay, so for this you calculate. Okay, here the distance is 2, here is also 2. Okay, so FBC times 2 equal to 0. Okay, so negative 100 times 2 plus FBC times 2 equal to 0. So you move to this, you calculate FBC is equal to 100 Newton. Sorry, this is not kilonewton, 100 Newton. Okay, this is positive, so it is tension. Positive means we assume the direction towards outward is correct. Okay, so I delete this again for clear message. So next, move to another joint. So we look at this joint of MC. Okay, so at C, so at this point, what is the forces that causes? So this one we already found is 100 kilonewton. So at this joint, what are the forces that will cause the bending moment? So of course you need to have forces and distance, force and distance. So you have 100, and then the distance now is 4 meter. So it is also counterclockwise, so it will have negative 100 times 4. Okay, and then what are the forces that will cause the moment? So FGC will not cause moment because this is connected to the C. So now we have another force is the FGF. Okay, FGS will have a bending, will have the moment caused, and then distance is 2 meter. That's why, and this one is also counterclockwise. We assume it going outwards, right? So negative 100 times negative GF times 2. Okay, so when you rearrange it, you calculate it, so you get FGF is negative 200 Newton. Negative means it is compression and means that it is not moving outwards from this point, but the force is moving this point. So the forces is doing like this, and this one just now the tension is like this. Okay, so now you got the FGF also, which is negative 200. Okay, so now you already found the two forces, and remaining one is FGC. Okay, remaining one FGC, you have two components, which is the vertical and horizontal component. Okay, so let's move to this. So now we can use the equation is total Fy equal to 0. Okay, you can see that you have this horizontal vertical forces 100 kilonewton, and then you have this FGC. Okay, the component for the vertical forces. Okay, so you have FGC, you can see that this is 2, okay, 2 meter, so this is theta. So tan theta equal to 2 over 2. So you calculate back theta, you will get 45 degree. Okay, so you get total Fy equal to 0. So FGC sin 45 degree, okay, going upward is positive, you assume. So this FGC sin 45 minus 100 going downward is equal to 0. So FGC is 141.42 Newton. Okay, so it is positive, is also tensile. So means that the force from the FG to C is moving upward. So it's correct. Okay, it's like this. Okay, so other than that, you can also do the checking back. You can substitute back this into this equation and then see whether it is correct or not. So this is a checking. So total Fy equal to 0. FGC sin 45 minus 100 is equal to 0. 100 minus 100 is 0. So it's okay. Okay, so this is the sections method that we use to calculate like the forces that you want at certain parts. Okay. So now look at the example 7. So determine the force in member CA. You want to get this one, CA, and then you want to get CF, and then you want to get FE. Okay, you want to get these three member forces by using the method of sections. So state whether the members are in tensions or in compression. So you need to determine the positive and also the negative. Okay. So this is going like this is going like this. Remember the shapes, the support reactions have been calculated. Okay, so the support have been calculated, and then the forces for this one is 3.2 kilonewton, and this is 4.8 kilonewton, and this is 6 kilonewton. Okay, these are being provided, so you can skip the step for the support reaction calculations. So we need these three forces. So how you can cut it? Actually, it's giving you a hint, so you can cut it from here. Okay, you will cut here. Okay, so you will see then which part you want to choose. As we said, we need to choose the part that we have least forces, so easier for us to calculate. Okay, so after you cut it, okay, after you cut it here, okay, so you can see that this one, when you cut it, then you draw it again from this one, you will get this is the point A. Okay, this is a point A, this is a point C, and this is the point F, and then this is towards E. Okay, so again the same thing. What you have to use you need to use the equilibrium equations. Okay, equilibrium equation is always will be used when you want to get the forces for the members. So when you try to find, okay, so here is a theta, so tan theta is 5/4. Okay, here is 5, here is 4, so you get theta equal to 51.34. Okay, so we can start calculate the moment from MC, which is this point. Okay, total MC is equal to 0. Okay, so what you can see that what is the force that will cause the moment here is this 6 kilonewton and this 3.2 kilonewton. And also where will it have? Here you have another one is the FFE. Okay, so this FAC and FAC and FC will not have any moment because they are from the joint C. They don't have distance from C, so it is 0 moment from these forces. Okay, so 3.2, this one is a positive. Okay, from this point this is the positive moment, so it is positive 3.2 times 4, plus also this is going this direction, so it is positive. It is causing the positive moment. Okay, and then FE is going to this direction, so when the moment occurred it is counterclockwise, so that's why it is negative. So when you calculate back, you will get FFE is equal to 8.56 kilonewton. Okay, in tensions, we assume it to be in this direction, and then it is also get with positive value, means that this is correct. Okay, so here these forces, when you calculate, it is 8.56 kilonewton. Oh, sorry, it's like this. Okay, in tensions. And then when you calculate, you want to get next value. Okay, so let us erase this first. Okay, so when you want to calculate at point A, which is the MA here, you want to calculate this point. What is the force that will cause the moment? Okay, so you will have it here. There's an 8 kilonewton force applied at here, and also the FSC. Okay, so for these two, we're not having any moment. So 8 times 4, the distance, minus FFC times 4 is equal to 0. So FSC is equal to 8 kilonewton. So here is 8 kilonewton. Okay, 8 kilonewton. Okay, so after you get this, and then now remaining is this one. Okay, you want to get these forces. So what you can do is, again, this one you can break it to two components. Okay, you can, the directions. You can break it to two components. Okay, you can break it to two components like this. Okay, you can break it to these two components when you want to calculate. So let me erase this. This is okay. So total Fy equal to 0. Okay, then you can see that what is the vertical forces here. You have it here 3.2. Okay, 3.2, 8 kilonewtons going downward. Okay, 3.2 8 kilometer going downward, and 8 kilonewton and new kilonewtons going downward. Okay, have these three, and then FAC is this one. Okay, FAC, and then you have the theta here, means it's a sin. FAC sin 51.34 equal to 0. So when you calculate and then you rearrange it, you will get FAC equal to negative 4.10 kilonewton. When you assume it is going upward, but then when you answer you get negative, means that the value, the direction of force is going inward to the joint, means that it is compression. Okay, so when you draw, it will have a compression here for 4.10 kilonewton. So it is in kilonewton, yeah. Okay, So this is the exercise. You need to do it by yourself to determine the member force of HI, okay, ID and also CD by using the method of sections. Okay, so you can try to calculate it. So let's move to another method, which is the alternatives method. And this one, the method is the one that I like the most actually. Okay, it is similar to join method, but then it is like in one picture, then you will calculate all. So let's look at this alternative method. Okay, so calculate the all member forces for this example. Okay, so what you can do is you're still using the same way you need to do. Okay, so for this alternative method, we will start calculate. Okay, we draw the truss, and then we will start to calculate with using the either start the joint at the easiest joint with only two unknown normally. Okay, so normally we start with the support is either support A or support B. So for this example, let we look at the support B. Okay, support B we have a 4.8 kilonewtons towards upwards vertically. So you can see that here we have a force towards EB, and here we have a force at diagonally FBD. So we can see that for these forces, it will have two components. Okay, so 4.8 is going upward, means that there is because this is in equilibrium, so total Fy equal to 0, total Fx equal to 0 for each joint. Okay, each joint. So for this is going upward, means that there is a force here going downwards to make this in equilibrium for the total Fy. So here is 4.8, so means here will be also 4.8. Okay, so 4.8 is going downward. So when you have 4.8 is over DE, okay, F is 4.8 over DE is equal to, then for these forces when we have the BD, okay, when we already found the vertical component, then we can get the horizontal component. Where we're using the comparison with this, you can see that 4.8 over DE is equal to X over EB. Okay, so 4.8 is over 5 is equal to X over X. So 4.8 is over 5 is equal to X over 4. So when you're using this method, you will straight away find that X is equal to 3.84 kilonewton. So you found another one here is 3.84 kilonewtons. Okay, so when you found this 3.84 kilonewton and 4.8 kilonewton, then you can using these equations to determine the forces of this. FBD is equal to square root of 4.8 at power of 2 plus 3.84 power of 2. So you calculate, you will get 6.15 kilonewton. So for these forces, okay, let we remove this. It's not clear. So you already found the component. Okay, let I redraw this again. So going this way is 3.84. Going here is 4.8. So also the same thing at the directions of it, it will become, this is 3.84 and this is 4.8. So the total at here is 6.15 in compression. Okay, so this is in compression. Okay, remember for the internal forces, this is compression and this is tension. Okay, so we already found this value. So also you have found the horizontal component at here is 3.84. So in order to keep this is in equilibrium, so the forces of this FBE will go into another direction from this 3.84. So this one is going to the left, then you get also 3.84 kilonewton. Okay, so when this is going toward the direction of E, so from the point E it will go to the direction of the P. So you get 3.84 at this value. So let me remove this so we will have a clearer picture. Okay, so after that, okay, then you can start to calculate at each point using the same equations, using the same method at each joint, and then you will break it to the components, okay, one by one. So from this point, okay, you can see that from this point you will have 3.2. So from point A, okay, so you can move to point A. Okay, point A, you can see that here you have 3.2 kilonewtons, and then you have another one vertical component which is from the FAC. So here you have a vertical component 3.2. Okay, so 3.2, you have it here. So you also automatically you can find the component of this. So 3.2, when you calculate 3.2, you 3.2, okay, you get the ratio, then you will get 6. Okay, so you can calculate also from these directions or another directions, you will get the same value. And then once you calculate that, this one, you get this, and then you can continue, you will get the value of this. Okay, so 3.2, you want to find it, is 3.2 over 5 is equal to x over 4. So you calculate, you will get x is equal to 2.6 at here. X is equal to 2.6 at here. So you will get this force. Okay, so 2, when you get the balance of 6 plus 2.6, okay, so you total it out, you will get this is 8.6 something. Okay, 8.6 if you calculate lah. Okay, so you can calculate from point A, point B, and then you can move it to another point. You can move to F. Okay, and then you can move to any point, other point also. Okay, you can go to 1.1 and then you will solve it. If you already calculate B, okay, calculate B, and then you want to move to point D, it's okay, because point D is also countable. You can see that this is this is 4.8 going upward, so here you will have a force 4.8 going downward, because here you only have horizontal force at here, vertical force at here, horizontal force at here, vertical force at here. So after you calculate B, you don't want to calculate A, you can go to point D. So let me remove all this so you will get clearer photos. Okay, so point D, okay, so this is 4.8, this is 3.48. okay, so once you calculate, here is in this system, this is going upward, so here it will going downward to be balanced, so it will be 4.8. so here it will be going this way, so it will going to the right. Okay, so it is also 3.48. okay, to make it balanced, 3.48. okay, so when this is mean it is in compression, as I said here. Okay, compression. So this is 4.8. okay, so you have also only at this point E, you want to go continue calculate from here. This is going up, so means that here will be balanced. Okay, one going up, one going down at this point. So here is also 4.8. okay, 4.8. okay, and then you have one forces here, and then what is the force here? You have also here as 3.48 just now. Okay, so and then at this point you need to calculate 4.8. 4.8 over dE is x over Fe. Okay, 4.8 over dE is equal to x over Fe. Okay, so 4.8 over 5 is equal to x over 5. So x is also 4.8. so here is also 4.8. so when you use the calculation of this, you will get FCE is equal to 6.79 kilonewton. Also here is in compression, 6.79 kilonewton. Okay, so here is 4.8, so here is also 4.8 kilonewton. Okay, same, because this is in one member. So here is 4.8 towards these directions, and here is 3.84 going this direction. So here the vertical and another horizontal forces will be total of these two forces. So you total it out, you will get x.64 kilonewton. Okay, so x.6, so when you calculate, you can see that here you have x.64. so to be balanced at 0.4, so here you will have another force at x.64 kilonewton. So this is in tension, this is in tension. So at this point, okay, F, you have a force at kilonewton, so it's going downward. So here for this point F, you will have 8 kilonewton going upward, because at this point you need to have equilibrium system. Okay, so this going outward is 8 kilonewton, so going downward is also 8 kilonewton. So after you calculate, you see you get this, all this you found already. Okay, then you only remaining one member. So for this one member, you can either use point A or point C to calculate. Okay, so you can use point A to calculate just now how I explained, and then you counter check with point C, you will get it in balance. Okay, sometimes the decimal point might be error secrets because we are having we use the 2 decimal point or 1 decimal points. If you want it to be more accurate, you can use up to 3 decimal point, but 2 decimal point is sufficient. So after you calculate everything, okay, at the final stage you will draw this diagram, just same as the diagram just now, but they are more organized. Okay, you need to draw out the direction of the forces to represent either it is C, 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 C. Okay, and then this is in tension, tensile, 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 tensile. So as we learned before, the top part will be in the compression, and then the bottom part of the truss will be in the tensile force. Okay, so what is the example I want you to practice by using automatic methods is, this is the example same as in the joint method. So you can use this automatic method to practice with this, the most simple example, okay, to do your practice, and then you can refer to the truss forces for each member by using the joint method example. Okay, so thank you for watching to my video. So we will carry on with chapter 3 in next video. So thank you.